So we can derive a few weak forms from the known equations we have. So for example, in the last lecture we already touched a little bit on boundary conditions, right? So let's actually derive the weak form of a Poisson's equation with some non-trivial boundary conditions. So let's derive this with u at 0 is equal to 0, but du dx at x equal to 1 is equal to, let's say, 1. So how does this correspond to the weak form? So to derive a weak form from this differential equation, and so here what we are going to do is we are going to derive the weak form from the differential equation and see how it is equivalent to the energy minimization form, right? So this is the PDE, and from the PDE you can go back and forth from the weak form, and from the weak form you can go back and forth from energy minimization. So this link works for some equations, doesn't work for other equations, and this link generally works for most of these equations. So this, I should put a question mark over here. So here we are going through this path, right? We have already, so up there, I'm showing this path. So to derive the weak form, what you need to do is you take a small variation on the solution u, and multiply the small variation, let's say delta u, on top of this differential equation, and integrate over this domain. Okay, so with this integration, we are splitting up this integration into two parts. The first part is delta u times the second derivative, and the second part is delta u times f. The second term is already a term in the weak form. We are going to pardon?
Because it's on partial u.
Yeah, so this is delta u, not partial u.
Delta u.
Right, so this is already as weak as it can be because it doesn't require any derivatives on delta u or anything. While here, this term is still stronger than what we'd like because it requires a second derivative on u, right? So to get rid of this second derivative u and thereby weaken the formula, we perform what?
Taylor series expansion.
No, integration by parts. Okay. So integration by parts again. So what does integration by parts mean?
The integral can be rewritten as the derivative times the integral in another part of the equation plus the part of the integral, the derivative of that plus the basic function.
Okay, so that's, I think, one way to state it. Anybody else has something,
Okay.
another way to say it?
Integral of u dv is uv minus integral of dv.
Right, that's another way to say it. These are good, but for me, it's basically taking derivative of one term and put it on the other term, right? So if you have two products and you have product of two terms, one is this, one is this, and one of the terms has a derivative you don't want, you can move the derivative to the other term. That's basically what integration by parts is like. And so basically after you do this, you get a negative sign. So the derivative is going to be moved to the delta u as opposed to be on the u. So you have one less derivative on u. Okay? Now, what am I missing in the integration by parts? So other than moving this derivative onto this function, I don't actually do it for free. There is an additional term I have to deal with if I do that. What is that additional term?
The integrated term of...
Yeah, it's the uv term, which after integral is the derivative, is the total derivative of u times v term. which after integral gets me to a boundary term. Okay, so the boundary term is here is delta u times the first order derivative, 0 and 1.
But you set your delta u such that it's 0.
Yes, my delta u at 0 is actually 0. Right, so this is because my u at 0 has to be 0. So any variation or any perturbation on this u has to also satisfy a 0 boundary condition. So what I have over here, the left boundary term. Oh, did I? No. Okay. So the left boundary term, the minus 0 part is gone. What I have left is delta u times du dx at 1 only.
Do we not have a boundary condition at 1?
Yes, we also have a boundary condition at 1.
Oh,
See?
right, okay, see.
Right? So how do we use that boundary condition here? It just becomes delta u, exactly. So it becomes, erase it. It just becomes delta u at 1. So the boundary term is very nice because after manipulation using all the boundary condition, it becomes something very simple.
So I'm sorry. The reason what was the boundary condition on delta u? Is it the u0 equals 0?
u0 equal to 0. So because u0 has to equal to 0 for so when I take a variation on u, when I make a perturbation on u, the perturbation, because the unperturbed and perturbed solution have the same boundary condition at u0, right? So my delta u has to be equal to 0.
Okay.
And that actually doesn't change if I have a non-zero boundary condition. If u0 equal to 1,
Then that delta u0.
delta u0 would be,
Because delta u is not perturbing the boundary conditions between the solution.
yeah, it's just perturbing the solution. So if u0 equal to 1, what is delta u at 0? 0, right? Because no matter what u0 is, my delta u at 0 shouldn't change that boundary condition.
Okay.
What if my u0 is equal to 100? What is my delta u at 0? Still 0, right? So the value of this Dirichlet boundary condition doesn't really change the boundary condition of delta u. Delta u at that fixed boundary condition is always 0. All right.
That's the one part of the solution.
Yeah, right. So you can, sometimes it's very easy to think of finite element from a structural perspective. Setting the solution at 0 to be a certain value is just fixing the structure at some point at a certain location, right? So what I'm saying is no matter where you fix it, the location of where you fix it is the value of the boundary condition, right? So think of the u as your deformation, right? So where you fix it is the value of the boundary condition, and where you fix it shouldn't change the amount of deformation, right? Which is always going to be 0. Okay, but this Newman boundary condition, which sets the derivative, it's not going to fix my solution at all. Instead, what we get is an additional term in the weak form, right? So my weak form becomes 2 integrals, right, plus a boundary term. All right.